We're going to start this section off by introducing the idea of a matrix. Now, we have already talked about matrices in the previous section, but that was in a very specific context, namely the augmented matrices of linear systems of equations. Now, matrices are interesting in their own right. They don't need to be associated with linear systems for us to want to study them. So here I'm going to introduce them just as an abstract object, and just keep in mind that while they can correspond to linear systems, they don't need to. Okay, so again, and I have already mentioned this, but let's just go through it again. A matrix is just a two-dimensional array of real numbers, or you can call it a rectangular array of real numbers. So let's take a little closer look at this one. So in this case, I've given it a name, or I've given this matrix a label. I've called it capital A. Quite often we use capital letters to represent matrices. And then here's the actual two-dimensional array. So you can see a whole lot of indices attached to the letter small a, right? So this here, we've got A11. Don't misread that as A11. That's actually, there's two subscripts that both happen to be equal to 1. So you should interpret that as A11. And then the entry over here, you can interpret that as not, don't think of it as A12, but A, rather than that, just think of it as A12. So the idea here is the first index is representing the row, and the second index is representing the column. So all of the entries in the first column here all have a second index of 1. So that's A11, it's in the first row and the first column. Here's A21, that's in the second row and the first column. And then all the way down to the very bottom, you've got now AM1, that's the last one. So it's still in the first column, but it's in the mth row. And the idea is that M represents the index for the final row or the last row. So actually, let's add something to this. Let's just add a little annotation. Let's say M is the number of rows. And I haven't officially said this, so let me say it now. The rows are the horizontal collections here. So all of these are rows. Rows are horizontal. So let's just add an annotation for that. So these are the rows. Now the columns are the ones that are vertical. So these are columns here. That's a column, that's a column, and that's a column. So let's label those to make it clear. So don't get confused between rows and columns. Just remember, rows are horizontal and columns are vertical. So M was the number of rows in this matrix, and in this case, N is the number of columns. You can see, I'll zoom in again here, you can see that N has been used as the index for the last column. So all those entries, or I guess I should say, all these entries are the entries that are in the nth column. Okay, so let's move on to some terminology here. And by the way, why am I using the letter A here instead of actual numbers? I'm trying to just stay as general as possible, right? If you actually have in a particular case where you actually are looking at a specific matrix, these A's, you could think of you'll replace them with actual numbers. Like it might be 0, 3, 2, -1, stuff like that, right? And then, so we'll get to an example in a moment. So let's read a couple of notes here. The first one here just indicates that you have some specific notation. If you want to refer to a particular entry of the matrix that occupies a certain position, you can use this notation here. I'm going to zoom in here. You can use this notation. So the idea is you just use capital A, because that's the name of the matrix, right? You would replace capital A with whatever you call your matrix. And then you put round brackets around it, and then you'll put two subscripts, an I and a J, although you'll have actual numbers in place of I and J. And the idea is I represents the row and J represents the column. So if I specify an I and a J, I really just mean pick out the entry that's in the ith row and the jth column. And based on what I've written up here, that's going to be precisely A sub ij, which was just the notation that we used for the entry that's in the ith row and the jth column. And we'll get to an example in a moment in case that's confusing. And the next thing I'll talk about is the dimensions. This is how we can talk about the size of a matrix in a sense. So the dimensions of a matrix, we just say, well, it's just the number of rows by the number of columns. Just like when you're talking about a room in a house, you might say that this room is 20 feet by 30 feet, for example. You're kind of doing the same sort of a thing. So in this case, if there's m rows and there's n columns, then we will say that the dimensions are m by n. That's what that's referring to. Okay, and the leading entry, every row has one, possibly. Every row might have a leading entry. Is it if you just read them from the left, start at the leftmost entry in each row, and as soon as you get to an entry that's non-zero, assuming that you actually do, it could be possible that every entry in the row is equal to 0. But if there's at least one non-zero row in that entry, then the first, or pardon me, if there's at least one non-zero entry in that row, then the first non-zero entry is called the leading entry. Okay, so let's look at an example. That'll give us an opportunity to clarify a lot of these things. So here's an example of a matrix. We've got a matrix here. We've called it A, and you can see it's got 2 rows. Here's a row, and here's a row. So it's got 2 rows, and it's got 1, 2, 3 columns. Remember, rows are horizontal and columns are vertical. So if there's 2 rows and 3 columns, then that means the dimensions are 2 by 3, right? 2 rows and 3 columns. Okay, well, let's look at the leading entries. What's the leading entry of the first row? Well, just looking at the first row, start with the leftmost entry and say, okay, is that equal to 0 or is it non-zero? Is it non-zero? Perfect. That means we got our leading entry. So the leading entry for the first row is equal to 2, because that's the first entry that's not equal to 0. Okay, and then what about the second row? The second row, you've got, well, you start off, there's a 0 here, then there's a 3. Ah, there, that's the leading entry, right? Because it's the first entry in that row that's non-zero. So we have a 3 there. Okay, and the rows, we can actually talk about specific rows. The rows of a matrix are actually, you can consider them as submatrices. So here's how I'll write this. The rows of A, here's the first row. I'm going to write it as a matrix. It's going to be a 1 by 3 matrix. It's got 1 row and 3 columns, technically. So that's the first row. And the second row, I'll write it as its own matrix as well. So 0, 3, and 4. So that's the second row of this matrix. Okay? So that's how you can break them down and look at them as separate rows. And you can do the same thing for columns as well. So there's 3 columns for this matrix. The first one is just the 2 by 1 matrix consisting of the entries 2 and 0. And the second column is the 2 by 1 matrix consisting of the entries 1 and 3, and then the third column is the column 0, 4. Okay, and this business here about referring to particular entries, this last line on our page is going to show us an example of doing that. So you can see what we've got here. We've got the notation here is just, it's the matrix A, and we want to pick out the specific entry that's in the second row and the third column. So if you go back up to the matrix A, here's the second row, and the third column is right here. So which entry occupies that position? It's going to be the 4. Okay, right? So that's how you can decode this notation here. So A23, which is I guess how you read that out loud, is equal to 4. That's all we're doing. So when we use this notation, we're just picking off certain entries from the matrix, one entry at a time.